Alright, so decomposition of metal compounds when heated, right? So metal hydroxide, carbonates, and nitrates. Metal carbonates
These are it.
and then we're going to go back to the reactivity series to just sum up this and then move on, alright? Alright, so the more reactive metals, the sodium, the potassium and the sodium, they
Calcium.
do not decompose. So, sorry, let me put it. So we're going to put the hydroxide, the carbonate, and the nitrate. Following? So this is hydroxide, this is carbonate, and this is nitrate. So for the potassium and the sodium, so when we heat it, it does not decompose. So it's a decomposition is that we are heating the compound, right? Same thing as heating the compound, right? The decomposition, I put thermal decomposition meaning heat, when we heat the compound, right? The hydroxide, so when I say hydroxide, I mean potassium hydroxide, sodium hydroxide, following? Or potassium carbonate, sodium carbonate, right? So do not decompose. So they are thermally stable, right? The nitrite, however, decompose to produce, the nitrate will decompose to produce the nitrite plus oxygen, right? Nitrate plus oxygen. Yes. Following? Then, so if we go from calcium, magnesium, aluminum, zinc, iron. So the hydroxide will decompose to produce the oxide plus water. So all of these. Remember that I'm referring to everything here, right? Let's set it sideways. Metal oxide plus water. Example. MgOH. Let's use to heat MgO solid plus water vapor. Alright? Following? Metal oxide plus water vapor. Right? This decompose metal oxide plus carbon dioxide. Example, calcium carbonate, not use, let's use calcium. CaCO3 solid. Alright? Good? Well, the nitrate will decompose to produce metal oxide, nitrogen dioxide plus hydrogen. Right? Metal oxide plus oxygen, right? Example, magnesium nitrate, right? MgO solid plus, let's see how to write a little bit. Right? Remember, nitrate is -1, so and magnesium +2, so we have to put bracket 2. Alright? Decompose to produce MgO solid plus NO2 gas plus oxygen gas. They can balance that their own. Do not exist. They basically do not exist. Basically, alright? Well, the silver nitrate decomposed to form the metal. Metal nitrogen dioxide plus oxygen. Okay? So just know that because it's so unreactive, it actually don't form, decompose the metal oxide, it goes straight to the metal. Right? So what's the general trend from the sketch that is on the board? Because the trend is to understand concepts, right? Groupon metals, which are the most reactive, they are very hard to break down. Right? Because remember that to break down a compound with a reactive metal, it simply means that you'd have to basically give back the potassium or the sodium, the electron, for it to go back in the metallic form. That almost never happens in life. Only process in which we could actually bring back sodium and potassium back to the metallic form is like electrolysis, which I'm going to discuss next. Right? When you have to use actually electricity in the molten solution of those salts. Alright? So as you can see, the potassium, sodium, they don't decompose. When you heat them, doesn't matter how high we carry the temperature of the hydroxide or the carbonate, they remain stable. They won't produce any carbon dioxide and oxide. The hydroxide and the carbonates, they are stable. Right? The nitrate, however, decomposes to produce the nitrite, which is not really the oxide, but it's another nitrate anion as well, except it's in the lower oxidation state plus oxygen gas. That's a little exception. So the main stuff from this table that you have to remember is the nitrates. They behave slightly different from the others, alright? So if you know hydroxide, carbonate, they basically behave the same throughout the trend. It's trend predictable. So all hydroxides and carbonate for potassium and sodium, they don't decompose. all the hydroxide and the carbonate for calcium, that's calcium, so group 2, group 3, and some of the transition metals, except silver, they will decompose to produce the metal oxide and water for the hydroxide, and the metal oxide and the carbon dioxide for the carbonate. So those are all group 1, group 3, and some of the transition metals. Alright? Again, the nitrate will go to the oxide, nitrogen dioxide plus oxygen. Group 2, group 3, and some of the transition metal. Okay? Silver, as we know, silver and gold would be down here as well. They don't exist. Because they basically tend to exist in the pure form. Alright?
That's why they made the term silver and gold vanish away.
Maybe. Alright, but I don't think that's the concept, but never mind. Alright? Alright, so let me just read through the objects of revision question for this chapter and see if you could actually manage. I'm not going to work them because we started late today. Alright? I want to finish by 7:30. Give 4 physical properties that are typical of metals. You're all comfortable to list 4 physical properties, right? Harding? Electricity, good conductor of electricity, heat. They are high density, they are solid at room temperature except mercury. They are malleable and ductile. Alright, those are what they're talking about, physical properties, right? Explain why metals behave as reducing agent in their reactions. Right? Even though we haven't covered redox reaction, they behave as reducing agent because they readily donate the electrons that they have. Alright? To reduce other compounds. Alright? Right. They readily lose the electrons. Alright? And when you lose electrons, you're actually the oxidation, the metal itself oxidation state going to increase, but the other component that is reacting with will be reduced.
What page that you're reading from?
Good. 157. Is it revision question from it, alright? Describe 3 different reactions which are typical for metals.
Mr. 3
reactions that are typical for metals. So the reaction with acid, water, or oxygen. That's what they wanted here. Right? And they are saying to write balance equation for each of the following reaction and name the products formed in each case. So zinc reacting with hydrochloric acid, magnesium reacting with steam, sodium reacting with cold water, aluminum reacting with oxygen. You have to know the general equations, then you can write those as examples. Alright? So let's move on. When we talk about reactivity series, we use, how did we put the metals in this series in the first place, in terms of the reactivity series? It's based on their displacement reactions and also on their thermal stability and the reactions that we have been looking at so far. Alright? So that is what we use to put them in this series. So we know that the group 1 metals, they tend to be very reactive and the compounds are very stable. Right? So the metal themselves, they are very reactive. The compounds that they form are very stable. That's for group 1 metals. Then group 2 next in line, then group 3, then the transition metals. Alright? But apart from the reactions and the stability, they also use another method to determine the reactivity series is the what we call the displacement reaction. Right? Displacement reactions, right? Normally, a metal that is higher in the reactivity series will displace another metal from its compound in solution.
That's
For example,
alkene.
look at zinc. Right? Zinc is higher than copper. Alright? You check the series, right? So zinc is higher than, say, copper or silver. Alright? Now, if we should have a solution, 2 solutions here. So in this one, we have say zinc sulfate, and in this one we have copper sulfate. Say we react the metal with sulfuric acid and form these salts. Alright? If we should put a piece of copper metal here, what do you think will happen here? Copper metal.
The copper, the zinc sulfate will dissolve.
Why?
It will dissolve
Yeah, why would it? Why do you think it would dissolve?
because the copper is a solvent.
Copper is a what?
Well,
No, that copper is a metal.
yeah.
We just
Yeah, I mean like it can break down.
So this would have no
Zinc degree.
displacement.
No displacement.
Yes. Right? But if we should put a piece of zinc solid in the copper, displacement will occur. So the zinc solid plus the CuSO4AQ is going to produce. Let me get some more space size. Right? It's gonna be zinc plus CuSO4 AQ solid produce zinc sulfate Q plus copper solid. Okay? So the zinc is more reactive than the copper, so it's gonna displace copper from the solution.
Oh.
That's what we mean, right? So this is a method in which they use to put the metals in the reactivity series as well. Alright? Alright, so next I'm going to discuss the general principle of extraction of the metals from their ores, right? Now, what do we mean by a metal ore? These are normally compounds in which the metals are found in the Earth's crust, right? We are quite familiar with bauxite
And gold.
mining. Well, in Jamaica, bauxite.
In Jamaica, bauxite.
Good.
But
Bauxite is actually what we're going to use to make aluminum.
aluminum, yeah.
So we're not going to find aluminum metal in the soil. We're going to find like aluminum oxide or sodium aluminum fluoride. Alright, so these are stuff that would form in the earth and we call them ores. Alright, ORES. Alright, so the process of manufacturing, like the process of extracting these metals from their ores will determine by the reactivity series, right? The more reactive the metals are, the more energy would be required to put them in their pure form, right? Alright, and then this is electrolysis. Alright, so I'm just going to draw the diagram to show. Alright, and this is how we normally get it in the exam. So I'm just going to draw the diagram and discuss it. Alright. So these anodes, they are made of graphite. Graphite, right? So all these are graphite, right? No, they have a steel case on the outside, or better they have this is a graphite cathode, right? So the positive and this is negative. Alright? And then on the extreme case, the steel case, outer part here is a ST. Alright? No. Remember that this is a solution, a mixture here, sorry. Alright, that's occurring here. So we have the electrolyte. Right? Which is the aluminum oxide, Al. Dissolved in is cryolite, or the aluminum oxide hydrate would be the bauxite, and the cryolite would be the sodium aluminum fluoride, which is F6. I'm just write the correct formula. 3 and 6, right? So this is aluminum oxide is really bauxite, and the sodium aluminum fluoride is the cryolite, right? Normally, why they mix both of them together in the reading, you'll find out that the aluminum oxide, which is the bauxite, it would have a melting point. Remember that electrolysis, we need to get this in the liquid form. So we'd have to heat this to get it in the liquid form, alright? Alright? The melting point of aluminum oxide would be like 2050 degrees Celsius. Alright? But the cryolite, which is the sodium aluminum fluoride, the melting point would be about 950 degrees Celsius, right? It's when we have that temperature 950 degrees Celsius, we can actually dissolve the aluminum oxide in the cryolite. So instead of wanting a temperature of 2000 degrees Celsius, we would actually use a temperature of 950 degrees Celsius to melt it and dissolve it in the solution. So you can see that we would use less energy, right, Hardin? Good. And then we have to know that the reaction that will take place is that so we know that we have aluminum 3 plus, oxygen minus, right? So yeah, so in the exam, you have to know the reaction that's taking place at the cathode and the reaction that is taking place at the anode, alright? Okay. 3 electrons produce Al liquid.
Plus what?
3 electrons. It is going to be supplied from the electricity that's going there at the cathode, right? So negative charge. So when we have a battery, you know, it's actually electricity going in one direction, the current going in the other direction. So like when you have a wire, electron is flowing in one direction, electricity is flowing in the opposite direction. So actually electrons are moving throughout the wire when we have a battery with electricity. Alright? While at the anode, oxide, liquid again, right? Produce oxygen gas. 4 electrons, right? So it simply means that at the anode, oxygen gas would be produced. Given off. Alright? So as you can see, as the aluminum is produced at the cathode, it will gradually fall to the bottom of the solution. So that is why this is aluminum. So this is Al liquid. And then we will just collect this off as pure aluminum. Right? So that is basically the extraction of aluminum. So you have the ores, ORES. Alright, so the bauxite, as I said before, it is Al2O3 X water, so it's impure aluminum oxide, and the cryolite is the Na3AlF6. So those are some that you have to know about the extractions of aluminum. And the reason why we use electrolysis in the extraction of aluminum, so let's say extraction of metal, we just want the pure metal from the ores in the earth. So the oxides and the whatever compound they're mixed in the earth with. Alright, that's what we use by extraction. Alright? So the important thing that you have to know for the exam is to write the equations at the cathode and the anode and to show the electrolysis. But remember that don't worry so much about this, because next year we are going to actually do electrochemistry by itself. So you're going to learn more about the cathodes and the anodes. So for now, you just take it as it is, that we extract reactive metals. So aluminum, this is the one that you have to know for the exam. But you have to also have a general idea, the same principle that all the metals above aluminum, so the group 1 and the group 2 metals, is electrolysis they use to extract them from their ores. Clear?
Yeah.